So in this particular section, we'll continue with our work in Unit 12. We've talked about entropy, now we're looking at Gibbs free energy. And there is a little bit of an overlap, if you remember, back to entropy, where we were talking about how a spontaneous process has led to an increase in entropy of the universe. So we can use that relationship to go exactly backwards, which means that in a spontaneous reaction, the entropy of the universe must be positive. Therefore, this expression must be negative. So that leads us to believe that for a spontaneous process, the change in Gibbs free energy, or delta G, is equal to a negative number. So that allows us to determine whether or not a reaction is spontaneous, or more simply, will a reaction actually go ahead? So with Gibbs free energy, there's a few relationships that are helpful. First of all, if Gibbs free energy is negative, or delta G is negative, the reaction is spontaneous. It's going to move down the slope towards the equilibrium point. If delta G is equal to 0, the reaction is here. Therefore, the reaction is neither going forward or backwards, or it is in equilibrium. If delta G is positive, approaching equilibrium from the other side, the reaction is only spontaneous in the reverse reaction, or it is not spontaneous in the forward reaction, non-spontaneous. So standard free energy changes. Once again, we use Hess's law, and Hess's law we've done for enthalpy and now entropy. And the final and third value that you'll find in your Appendix C is delta G values, or Gibbs free energy, or just free energy. So when using these values, you'll be dealing with kilojoules per mole again. And if the delta G of the overall reaction is negative, it tells you whether or not the reaction is spontaneous at standard state. You'll notice that the degree symbol is there. So that's standard conditions. So when we work and start to try and predict this equation, this probably becomes one of the more useful things in thermochemistry for us to predict whether or not a reaction is going to happen. The first term we see there is the enthalpy term, so that is the enthalpy of the reaction at standard state. And the second term we see is what we call the entropy term. And the entropy term is the product of the temperature, the absolute temperature in Kelvin, multiplied by the change in entropy of the system. So the thing to understand is that Gibbs free energy is temperature dependent in most cases. So we need to come to terms with the fact that a reaction can be controlled by either enthalpy or entropy. So since only one of those terms actually has temperature assigned to it, the entropy term, then generally entropy is going to be what controls whether or not a reaction is spontaneous at a specific temperature. So we look at this particular table, and this table is very good to just be familiar with and know, only because it allows you to answer or predict whether or not a reaction will be spontaneous at set conditions without really doing a lot of work. So for example, if a reaction has a negative enthalpy and a positive entropy, the reaction will be spontaneous at all temperatures. If a reaction is positive enthalpy or endothermic and a negative entropy, then the reaction is non-spontaneous at all temperatures. It will not work. If both enthalpy and entropy terms are negative, it is spontaneous at low temperature, non-spontaneous at high. And if both terms are positive, it's spontaneous at high temperature and not at low. So because we're talking about free energy and whether or not a reaction is going to go, really we're talking about forward and reverse reactions. In other words, we're talking about equilibrium. So under any conditions, the standard or non-standard, the free energy change can be found using this equation. This is the second equation that really does get us a lot of use. So the first thing is that under standard conditions, one of the definitions for standard conditions is that the concentrations of all solutions are 1 mole per liter. Also, all gases are held at 1 atmosphere. And obviously, we call those standard conditions. So in a case where we are at standard conditions, the law of the reaction quotient, which we recognize as Q, is going to be equal to basically 0. So we end up with delta G is equal to delta G standard. So it's only when those concentrations are non-standard that we start to see some deviation from what we had predicted using appendix C values. So at equilibrium, Q is equal to K, and obviously delta G is equal to 0. So we can kind of start subbing reactions into there. So we set delta G equal to 0 at equilibrium by definition. And again, this is a very, very big idea. And we see that we can actually then substitute in the K value instead of Q. And now we have an equation that we have down here where we can actually determine what the reaction the equilibrium quotient or product is. So K is equal to e to the negative delta G over RT, and that's delta G standard state. So now we have a way of looking at Gibbs free energy, which we have to set to 0 at equilibrium to find the equilibrium constant. If delta G is not set to 0, this doesn't work, but that would mean that the reaction is currently not under equilibrium conditions.